next speaker is Andrés Sotomayor, correct? Yes, okay, we can see your slides, and he's going to tell us all about CMS.
Okay, muy buenas tardes y saludos a todos. Hello, my name is Andres. I'm based here at CERN. I'm in Building 40 right now. And I'm hoping that I can give you guys a sense of the most recent results coming from CMS and future prospects. So this will be a quite comprehensive talk, but I think what I would like to communicate is just the wealth of results that are being published and just a sort of outlook towards the future. So I have just an outline here, and in particular, I'd like to, I split this into standard model and then beyond the standard model results. And within those, there's several categories. So we'll go along and discuss one or two analyses per each of these categories. And as I said, I would like to present a look towards the future. And with that, I'm gonna go ahead and get started. So I will be pretty brief with the results. I have many results, but I'll try to give you just a sort of bird's eye view of, of what I would consider very interesting, very recent results from CMS. So slide 3 is sort of an introduction to the LHC. I don't think it's needed. I'm just gonna go ahead and skip to the schedule for the LHC. And the schedule was updated this year, but this is a very long-term schedule. As you can see, it goes all the way to 2036. And this schedule will be adjusted as we go along, but I was hoping I would sort of locate you in where we are in the schedule. So we just came out of the second long shutdown, and this was a period of upgrades and maintenance. We'll come back to this, but what we expect, or we're at least hoping for, is to actually start collisions or what we're calling run 3 during next year, hopefully early next year. And this will, as you can see, extend over a couple of years. Then we have another shutdown with more upgrades, and I'll come back to what these represent. These are very major upgrades. And then we hope to have physics all throughout the next decade or so. So I have a slide on CMS. I don't want to spend a lot of time here, but which reminds me that I need to start my clock. So CMS, I just wanted to give you a sense, in case you're not familiar, perhaps distinguish it from Atlas is one of the things I would like to do. So one of the more striking features and unique features of CMS is that we have this single magnet, this superconducting solenoid, which you can see here. And you can imagine this as a very large cylinder that's about 6 meters in inner diameter. And it contains all of the tracking and the calorimetry. So this is something that's very unique. This magnetic field is strong enough that we can contain or keep all of the tracking and calorimetry inside. And then outside of that magnet, we have mainly the muon system. So it's a general purpose detector, and this comes back to what I was saying. We have a wide variety of results that I'll try to summarize. But before we get to that, I just wanted to mention that I think most of you might know the size of the collaboration is very big. So actively, we have around, let's say, more than 5,000 people, and many physicists, many engineers, over 200 institutes around the world, over 50 countries. So I'd like to give you, all of the results that I'm going to show today are going to be, let's say, analyses that cover all of the data acquired during run 2. And what you can think of the LHC performance, right? So the LHC has actually been operating at twice the design luminosity. So the peak luminosity has been twice its design value, which is fantastic for us. And that represents about 160 inverse femtobarns of just proton-proton collisions at 13 TeV. Now, from the point of view of CMS, we try to take as much data as we can. We're looking at something, let's say over 92% of data taking efficiency. And that represents about 137 inverse femtobarn that we declare sort of good for physics. So using that data, CMS at this point in time has submitted more than 1,070 papers. We had a bit of a celebration for that 1,000 paper. It's quite the accomplishment. And yeah, the rate of publications is steady and perhaps even growing a little bit. I mentioned we are in the middle of, well, we have upgraded the detector in preparation for run 3, and I will discuss the sort of long-term upgrades as well. So I think it's maybe very helpful. As I mentioned, I'm going to go very quickly over many results, and something that I perhaps might help is that I include in the slides link to a list of, or the list of publications where you can find the papers themselves. There's also a very, very useful search page for CMS, and you can sort of tag or filter whatever topics you're interested in. It's a very, very specific and very helpful search. And finally, I also want to advertise what we call the public briefings. So these are less technical summaries of some of the recent results, and you can find these on the CMS website. They're very I find them a very nice way to learn about new results, and you're welcome to check it out. I would say actually a lot of event display photos, as you can see some of them on the left, a lot of them come from these articles, so they're an excellent resource. So with that, I'd like to jump in and first talk about the standard model. This slide 10 here is a very sort of condensed picture of many, many results, right? So I've tried to make this clear by what we're looking at. What we're looking at is the production cross-section in the y-axis. And then there's many, let's say, categories, I guess. We have electroweak, but within electroweak, you can look at single vector boson, double vector boson, or even triple vector boson processes. And you also have vector boson fusion or scattering. And then in sort of highlighted in red, you can see some of the top results and for the many different channels. And finally in blue, we have some of the Higgs results. So as I mentioned, this is really just a summary plot. We'll dive in and look at some of the more detailed results that have come out of the experiment. So starting up, I have this result. It's a measurement of the C invisible width. And it's actually it's the first measurement of its kind at a Hadron Collider. So this kind of measurement was done at the LEP experiments. And CMS has actually managed to come out with the most precise direct measurement of the C invisible width. So it's, as I said, it's competitive with the direct measurements from LEP. And the way this measurement is done is that there is a simultaneous fit to data regions that contain C invisible and then C to leptons, where these are electrons, are muons. And you can see on the bottom left here, you can see the missing energy or missing transfer momentum distribution for these different channels. So you see the missing transfer momentum plus jets, and then in the middle you have the muons, and then electrons on the right. So I'll move on to B physics, and we have a very, very interesting result. Actually, the first thing I should mention about this result is that in the week or so that I prepared the slides, this result, this paper has been submitted to Nature Physics. So it's in the process of the journal peer review. And this is a very, very interesting result. It's the first observation of triple J psi production. And it's it's significant in excess of 5 standard deviations. So it considers contributions from single, double, and triple parton scattering. And the final state is found to be dominated by double and triple parton scattering. So you see in the bottom, you have the dimuon mass distributions for different amount of energy in the final states. And I'll just mention that there's a comparison here in the middle figure here. You can see this result in black, and compared to just many other CMS, Atlas, and even D0 results from double JSI or vector JSI, and then WJETs, WW, and so on. So I do have one result that I would like to highlight from heavy ion. And for CMS, this is the first observation of the B sub C plus meson in lead-lead collisions. In particular, this is looking at the leptonic channel. So the JSI decays to 2 muons, and then we have an additional muon. This particular meson is interesting. It's the only one containing 2 different flavored heavy quarks. And this provides a unique bridge between Chermanian, Borumonia, and heavy, open heavy mesons. So it's an insight into the interplay between suppression and enhancement mechanisms. And you can actually see this analysis uses boosted decision trees. You can see 3 of these low, medium, and high bins. And you can see in the triple or tri-muon mass distributions for each of these bins. Okay, so I would like to jump into Higgs physics, and I have several Higgs physics results that I would like to summarize. But first, I would like to give you an overview of, let's say, slightly chronological overview of the Higgs. So in 2012, as I'm sure you remember, we announced the discovery of the Higgs. And what we saw is a particle that's consistent with spin 0. And we were able to do a mass measurement at the 0.2% or so. Now, at the time, we saw couplings that were consistent with standard model expectations. And by the end of run 2, we were actually able to observe all the main production mechanisms. So that's gluon-gluon fusion, TTH with in association with top pairs, vector boson fusion, and Higgs in association with a vector boson. So we are also able to see or observe Higgs decays into bosons and 3rd generation fermions. And I will most certainly come back to this in the next slide or 2. And at this point in time, we have an excellent mass measurement right around the 125 GeV mass. Now, one of the main messages, however, is that all measurements that we have done so far are consistent with standard model predictions. So let's look at some of the results in more detail. So I would like to start with an observation of Higgs decaying to a pair of muons. So this is the first evidence of Higgs coupling to 2nd generation fermions. And in this particular analysis, we have an observed significance of 3 sigma, where we expect around 2.5. And this is a very challenging analysis, since the branching fraction is 2.2 times 10 to the minus 4 or so, and it has a large irreducible background from Z to dimuon. Now, this analysis considers all the production categories that we've mentioned previously, and it's a very important result, I would say. As I mentioned, it's the first evidence of Higgs coupling to 2nd generation fermions, and this nice picture on the bottom right shows the coupling. These are ratio standard model you see at the bottom for Higgs decaying to tops to vector bosons to B quarks, taus, and then at the bottom left of this figure in green, you can see the muon here. So it's a nice addition and very interesting to be able to make this measurement for Higgs decay to muons. Next up, I would like to summarize a measurement of the cross-section for Higgs to tau-tau decay. This is an inclusive and differential cross-section measurement, but in particular, it's the first differential measurement of Higgs to tau-tau cross-sections. And this analysis also integrates over all of these Higgs production modes. It considers tau decay into leptons and also hadronically. And in particular, it focuses on the Higgs momentum distribution, the jet multiplicity, and the leading jet momentum. And you can actually see these distributions here at the bottom left in these figures. There's significant improvement over measurements in other final states, events with large jet multiplicity or Lorentz boosted Higgs boson. So I'm gonna move on to a search for Higgs BB. So this is a di-Higgs search, and di-Higgs production in particular exploring several couplings. So this it uses a dedicated HL2 trigger that's a high level trigger with 3 B jets. And in particular, it targets gluon-gluon fusion and vector boson fusion. And it employs a new multivariate analysis strategy. So there's a new background estimation methodology from multiple control regions. And you can see kind of a hint of this in the bottom right. You can see at the top, these are gluon-gluon fusion using this BDT or boosted decision tree output. And at the bottom, you see, in particular, vector boson fusion. You see the di-Higgs mass distribution here. So these are consistent with standard model expectations. So we proceed to apply limits here. I do want to point out that in particular for the kappa 2V, there's a better limit that has been recently published by CMS using BBF boosted HBB analysis, which I can talk about if people are interested. It's in the backup slides. So I have two top analyses that I'd like to highlight. First, we have an analysis where we probe effective field theory with TTZ. So this is focusing on events with top pair production in association with a Z. And we search for effective field theories in top quark interactions. Now, as I mentioned, there's an associated 1 or 2 top quarks associated with the C boson in multi-lepton final states. So when we have 3 or 4 light leptons, we divide that into signal and control regions. And the analysis interpretation, as I mentioned, is an effective field theory. So it uses these dimension 6 operators, and it also considers relative Wilson coefficients. So this is one of many. In fact, most of these analyses are employing machine learning techniques in some way or another. But this one in particular is, can optimize the sensitivity for each of these EFT parameters. So I'm gonna jump ahead. I have another another top analysis that I'd like to highlight. So here we are interested in a measurement of the TT gamma cross section, and these sort of production where you have top pair plus X, it provides a direct probe into the top quark couplings, and these can be modified in many beyond the standard model. So we'd like to see if these are consistent with standard model expectations. So this analysis is measuring it looks at a top quark pair in association with a photon, and it's a measurement of the cross section. We have, or we consider one highly energetic muon or electron, one isolated photon, and then 3 or more jets, one of which is tagged as a B quark jet. So this analysis sees pretty good agreement with the standard model expectation, and we have the differential cross sections in different, let's say, variables are measured and interpreted and under EFT models. So at the moment, it's the most stringent direct limits on anomalous electromagnetic dipole moment interactions. All right, so let's jump into beyond the standard model. So I have a few results that I would like to highlight here. And again, there are sort of several subcategories for beyond the standard model. So first up, I'd like to talk about what we call beyond 2 generations. So this is a summary plot. You can see there's a wealth of analysis here. Of course, I couldn't possibly discuss all of these. If you're, by the way, if you're interested in these, there's a link. Usually I include a link to these results, and you can go and look in more detail at these results. But for the time being, I would like to focus on one of these analyses, a very recent result from CMS. which is a search for resonances decaying into triple Ws. So in particular, this considers a search for decays via scalar radion. And you can imagine some kind of resonance that produces a W and this scalar radion, and then that can decay either into two Ws, or you can see from these sort of quasi Feynman diagrams, it could also sort of combine it. So you could have in total 2 massive or 3 massive Lorentz boosted jets. So you can actually see at the bottom left here, there are 6 control regions, and you can see the dijet mass distribution for these control regions, or signal regions, I should say. And these results are combined with a complementary search in the lepton plus jet final states. So the limits that you can see in the bottom right, these are on the left all hadronic, and then on the right, these are combined with a single lepton search. So I have, I think, 2 analyses that are part of the subgroup that we call Exotica. And we, as before, I have, again, I should say, there's a large number of results that have been published by CMS. And this is meant to be a summary plot of these results when they exclude whatever signal they consider. So again, I'm going to just consider one particular analysis here. That is a search for long-lived particles decaying in the CMS muon endcap. So there has been a lot of interest recently in long-lived particle searches. These are, of course, very challenging signatures. And this is sort of, many people say we have to turn over every stone and search everywhere. So this is one case where there's a lot of innovation, and we sort of use the detector in a way that is unusual, and it wasn't really designed to be used in this way. So the idea here is that we look at, or we consider a Higgs perhaps decaying into 2 neutral long-lived scalars, and then those can decay into B quarks, D quarks, or tau leptons. So we actually come up with the most stringent limits for this kind of branching fraction for Higgs to these 2 long-lived scalars to the heavy quarks or taus. And as I mentioned, we are using the detector in a very novel way. We are actually using the muon endcaps, the CMS muon endcaps, as sort of a sampling calorimeter. So we can sort of look in the muon system and see if we can spot these sort of spontaneous decays of quarks or taus. And so these hits in the CSC, which is the cathode strip chamber detector in CMS, these are clustered using the DBS scan algorithm. And this method is validated using C events, where one of the muons undergoes Bremsstrahlung in the endcap. And the photon produces an E&M shower. So I have another long-lived particle analysis that I would like to highlight. This one is a search for Higgs to long-lived, or Higgs decay into long-lived particles in association with a C boson production. So here you can kind of see from the Feynman diagram that we have a Higgs that decays into these long-lived particles, and then those hadronize. And this is produced in association with the C boson decaying leptonically. So we expect at least, from this signature, we expect at least 2 displaced jets. And we use the 3 track-based displacement variables. And we're considering both light and heavy jets, so down and bottom quarks, for this analysis. So the benchmark model here is Higgs decay to a pair of scalar long-lived particles. And this analysis probes from around 1 millimeter to 1 meter, and this refers to the proper decay length for this analysis. Okay, so moving on, I would like to highlight SUSY and the status of supersymmetry. There's many searches in supersymmetry. So I'm hopefully giving you a sense of the most recent constraints. from this summary plot, but again, I encourage you to either click on the links or just have a look at the more recent supersymmetry results from CMS. I have one analysis here that I would like to highlight, and this is a search for top quark in compressed spectra. A lot of the SUSY parameter space has been pretty much ruled out. So we are still interested in signatures where we have compressed spectra. That means that the mass differences between parent and perhaps the LSP are small. So the stable particle and the parent particle are close in mass. And this particular analysis is interested or concerned with signatures with 2 or more jets and large missing transverse energy. So the events are categorized into 0, 1, or 2 leptons. And this analysis uses a deep neural network algorithm to separate signal from background. So the analysis includes a dark matter interpretation. It's a Decay BS spin 0 mediator in association with a top pair. At this point, I would like to switch gears a little bit and talk about future prospects. As I mentioned, the LHC and CMS is just coming out of this period, what we call the second long shutdown, and it's getting ready for run 3. So we have at this point finalized preparations in CMS. I outlined here just a few of them. We have the installation of the beam pipe, which you can sort of see a picture of here. And this is a phase 2 design. That means that it's a smaller diameter beam pipe that will be small enough to fit the next generation pixel detector, which will be used a number of years from now, or will be installed a number of years from now. So the current pixel detector at CMS is a 2nd generation pixel detector. We call this phase 1, and it was just reinstalled. There were some refurbishments, let's say. So the DC-DC converters were replaced, and it includes a new first layer for that detector. And I also had to definitely include work that I did with the luminosity group at CMS. So we haven't rebuilt 2 detectors and just installed them. There's 2 more important upgrades. So the hadronic calorimeter for CMS has completed its readout upgrade. And we also have a brand new Muons subsystem at CMS. It's the GEM subsystem. And we have the GE11 chambers installed. This is a gas electron multiplier system. So in preparation for run 3, there's many things that, again, not just in terms of hardware, but also in terms of trigger and HLT. And I definitely have to mention that we just completed what we call the LHC test beams or pilot beams. So this was a period of about 1 to 2 weeks where we had stable beams at injection energy. So this is, we're talking about 450 GeV per beam, but we did have actual collisions. And that means that we had to run the whole detector, including these run 3 upgrades. So it was a great way to prepare for run 3. And as part of those preparations, I mentioned the DAQ and trigger, HLT in particular. One of the biggest upgrades is that we are moving into a mix of CPUs and GPUs in the high-level trigger, which has a lot of advantages in terms of just the tracking out the trigger algorithms, and it's also sort of a sort of test bed for high luminosity LHC. And I should really mention also that we have an increase in data scouting and data parking in particular. This, I think, will become important in many searches. And we have implemented dedicated and improved long-lived particle triggers, which are a lot of people are very interested in. So I'd like to discuss a bit about high luminosity LHC. I suspect most of you are familiar with the program, but the goal here for high luminosity LHC is to, again, have a number of years of upgrades and maintenance to the detectors, but also to the LHC, so that we can essentially increase the luminosity, instantaneous luminosity, by a factor of 7.5 or so. So it's almost a factor of 10. That means redesigning and installing many, many upgrades. So I would just like to give you a hint of what is planned for CMS. So these are what we call the phase 2 upgrades. And at this point in time, CMS has prepared many of these technical design reviews. You can actually, there's a link to them and you can find them in CDS. These are lengthy documents that basically propose these upgrades, or detail the upgrades and what we expect. Now, I will just highlight a few of them. I don't really have time to go into all of them, but the tracker is going to be brand new, and one of the striking features that hasn't been possible until now is to have a level 1 trigger. So this next generation pixel detector, we expect to have to contribute to the trigger firing or the trigger in level 1. So for the let me just mention the MIP timing detector. This is also a very exciting detector. So we expect to have precision timing from crystals and silicon photomultipliers. These should allow us to decompose, let's say, well, we expect much higher pileup. So that means a much larger number of interactions per bunch crossing. So this should allow us to untangle all that information. And I can't not mention the endcap calorimeters. These will be replaced completely. And these will include silicon and also calorimeter sections for these detectors. So just my last couple of slides are going to be on the prospects, the physics prospects at the high luminosity LHC. So the slide, it actually summarizes 2 different projections or analyses involving the Higgs. So we expect the high luminosity LHC to facilitate precision measurements of the Higgs coupling, and except for the rarest couplings, we expect to constrain the Higgs couplings to the less than 10% level, which should allow us direct access to the Higgs potential shape. And I also should mention the di-Higgs production observation is a flagship measurement. So we expect to achieve at least 3 sigma observation. So we should see some signal there, expected from a combination of channels. So I will move on to what I believe is my last slide. I also wanted to mention just another analysis. So this is a mono-C search for dark matter, and this is the prospect for high luminosity LHC. So this, I should say, this and the previous analysis are both considering an integrated luminosity of 3000 inverse femtobarn, which is sort of the baseline for these studies. And we expect to, of course, a generous increase in the sensitivity and exclusion power in searches for new invisible particles. We hope to push the sensitivity to large dark matter masses and push down in couplings. And this kind of search, hopefully, we expect it to extend the sensitivity of mediator masses by around a factor of 2 relative to current LHC results. So I just have a quick summary slide, which again is, just an overview of what we just discussed. CMS and LHC are performing very well, or certainly have performed very well during run 2. And the preparations for run 3 are nearly completed. And we are, of course, preparing for beyond run 3. So I hopefully gave you a sense of the wealth of results that CMS has harvested from the run 2 dataset. Again, the Higgs measurements that we have done are consistent with standard model expectation. There's no new sign of new physics at this point. And we have completed the installation of testing for these run 3 upgrades. We're ready for data taking next year. And looking forward to high luminosity LHC, we know this will provide an unprecedented data set. We have prepared, as I mentioned, all these technical design reports. These are all been reviewed and are ready for the next step. And we hope that this data set, this high Lumi period, will further characterize the standard model and expand the search for new particles and interactions. So that's it from me. Please let me know if you have comments, questions.
Thank you very much, Andres, for this complete report. I think, as you mentioned, it's impossible to cover all the subjects because, well, so many papers and using the full run to data. That was an amazing year indeed. So we have time for questions. Joel? Yes.
Hi, can you hear me?
Yes.
Hello, yes, hi. So could you go back to your slides about long-lived particles? I think it's slide 32 or so. Right, so you have this one on the, is this search on the CMS endcap. So why do you use the endcap and not the whole muon system?
So in this particular case, you're, just to make sure we're on the same page, so you're looking for long-lived particles. So what you might have is a particle that you don't detect until it traverses part of a significant part of the detector, and then it decays inside of the detector. So the reason we use the muon detectors, it's because it's at the outer part of the detector. I don't know if the question is why we use the end cap instead of the barrel. Yeah,
that's the question. Why the end cap and not the barrel?
So I'm not certain if this has to do with the validation method. So I can double check, but I suspect this has to do with the validation method where you can sort of, I mentioned here, you have one muon that you can measure in the end cap if it undergoes bremsstrahlung, and you produce a photon, sorry, the photon produces a shower. But I can double check and get back to you.
Okay, yeah, I appreciate that, even the Slack channel. Thank you.
Okay, yes, Ignacio, please.
Yes, you showed 3 J-psi finer states. Can you show again? Yes, LHCb found beautiful, or at least evidence of the resonance of 4 CC bar quarks. Looking just in J-psi finer state. Did you search for this decay? Since you have 3, maybe you can look at 2 J-psi producing a finer state, a resonance.
Yeah, so as far as I know, this particular analysis didn't consider this this final state. But I think, just as a general note, I hope CMS can really, we need to become more competitive with LHCb. But as far as I know, it is not considered in this search, and I'm not aware of a dedicated search that has published results yet. But I'm sure if I asked around, somebody is definitely working on this at CMS.
Okay, thank you.
Yes, Rogelio, please.
So thank you, Andres, for the very nice talk. Just a quick question. Do you have any results on the Higgs width?
Yes. So unfortunately, I don't have these in the slides. Unfortunately, I wish I had them in the backup slides. But the same way that we have these results, maybe I should re-advertise the fact that we have a very useful public results page. So unfortunately, I don't have much to show you in the slides, and I don't recall off the top of my head what the most fresh results are for the Higgs width. But I can certainly point you to the paper, the most recent publication for CMS.
Okay, thank you, Andres.
So is there any other question? So one thing that you mentioned, this search for resonance states in the 3W channel, and yeah, so you jump directly to the search, but I would like also to know about the standard model 3W production. That for sure, you know, this was one of the highlights of the year. So can you tell us something about that?
So I believe this is part of what this complementary search in the lepton final state is. But I don't, yeah, this is another analysis that I didn't look at carefully since I don't have it in the backup slides.
Yeah, but I mean, as part of the standard model, not as a search, because it's a 3W production.
Well, let me see if this is actually, so I mentioned, yeah, actually you can see this.
Yeah, you have it there in the briefing. Okay.
Yeah, so this is, again, I would recommend if people are interested, there's a very nice article from Freya Blickman. And in fact, this became, if you actually type on your web browser, you type www.triboson.cms.
Yes,
it takes you to this article.
Of course. Now this I know, but since it's one of the highlights of the year, but okay, you mentioned it there.
Yeah. So this almost made it into the talk, but unfortunately I didn't have time.
Yeah, I know it is impossible. And just a tiny technical question, since you show all these beautiful results, including JPSI, that means that you have really a very good performance at low PT electron and muons, right? Can you tell us about that? Because I think it's quite special in CMS.
Yeah, so this, of course, is something that has been improved throughout run 2. So the low PT performance, I'm trying to think if there's a particular search here that I can point out. But yeah, anytime we talk about lepton reconstruction, we can talk about improvements, and also in Higgs result. This is where a lot of the, let's say, more sensitive results come from, is that improvement in the reconstruction for low PT leptons. Yeah. I wish I could find a kind of a very specific example from here, but I don't think I can sort of use it, one of the analysis as an example. Sorry to.
Yeah, no, that's fine. I mean, I understand with all these nice results you show with JPSI that that is the case in CMS, very good performance at low PT electron and muons. So yeah, we can infer that from your results. So that's okay. Okay, so I don't see any other hand. So we thank you again. Thank you very, very much. We know that this